Okay, this is your lesson for Friday. It's the review of chapter 3, and if you want to rewatch it Monday or practice some more problems Monday, you can, so that we can move forward with the test on Tuesday. All right, so the first section is about classifying a system of equations as independent, dependent, or inconsistent. And the independent and dependent are both consistent, meaning they have a solution. Independent means you got two lines that cross, hit at exactly one point, and there's just one point, like an independent person's one person that can do whatever. Dependent means those lines depend on each other. They're basically the same line is what it is. Every point on this line is also on this line. Okay, so let's look at these real quick. If you look at the first one, number 3, we could rearrange this to put the 6x right here. If we moved this y over, it'd be 6x minus y equals 2. You could also rearrange it slightly differently so the 6x's were by themselves. In fact, I probably should use actual whiteboard to work on this. So with that first one, if I wanted to rearrange that, 6x minus 2y equals 2. If I wanted to put it in like a normal slope-intercept form, I could rewrite this as, first let me divide everything by 3. And then let me move everything around. So 3x, I'll move the 1, move the y. Alright, so this would be it in, I mean, obviously I usually put y equals, but whatever. So this is like the first one. The other one, 2 plus 6x equals y. That's kind of already in the right format for me, right? If I wrote it in normal slope, ooh, it's messy. And that got worse. In normal slope-intercept form, it would look like this. These have different slopes. The 3 and the 6 are different. So if I have 1, it would be like up 3 over 1, up 3 over 1. The other one would be more like up 6 over 1, something like that. They also have different y-intercepts, but the important thing is they have different slopes. If they'd had the same slope, that would mean they're either parallel or they're on top of each other. The fact they have different slopes means they're going to lean at different angles. That means this is independent. Alright, so let's look at the next one, number 4. Let's quickly rearrange this. So we're going to put 2x, and then we would subtract the 5, and that would be a negative y. But to make the y positive, I just need to swap everything else. And then the other equation is, so it has a negative 3y, so I'm going to put the y on the side. And then I'm going to divide everything by negative 3, so that becomes negative 2x. That becomes positive 5. Aha, and look what we have. So number 4, these are dependent. They're literally the same line, just written differently. All right, let's do number 5. So some of these you can kind of tell, and it's a little bit easier, especially if you act like you're about to solve them using substitution. So like for number 5, let's divide everything by 2. And then for the bottom, let's divide everything by 4. Okay, so if you solve these using elimination, I mean, we could graph this or we could rearrange it so they're in y equals so you can easily see the slope, but you can kind of see what's going on. If we move the x to the other side on both of these, it's going to become a negative x. And then if we divide everything by 3, so the y is by itself, both of those negative x's are going to become negative 1/3 x. In other words, they have the same slope. But the 1 and the 4 make it different. They have different y-intercepts, so it's essentially like negative 1/3 slope here and then a negative 1/3 slope here. So we can tell if we rearrange them that the slopes are the same, but the y-intercepts are different. So they're parallel. That means this is inconsistent. There is no solution. But you could also kind of imagine like you're going to do the method of elimination, and you were going to multiply everything on the bottom by negative so that you could work through that, and that would eliminate the x's, but it also eliminates the y, so you'd end up with 0 plus 0, which is 0, equals 3. Is that true? That is not true. So we know that this is inconsistent. We can figure that out by trying to solve, like thinking about it with elimination, or we can think about it by comparing the slopes. Do you get the idea? Number 6 is not really kind of fun looking, so I'm going to actually multiply everything in that by 2. So 1.5 times 2, 3 times 2, and 1/2 times 2. And then the other one is 6 minus 2y equals -12x. I'm going to rearrange things. I'm going to put the 12x on this side and the 2y on that side. I'll keep the 6. So I just added 12x to both sides, in case you're like, what just happened? And then I added 2y to both sides. And that caused this to go away. That caused this to go away, so that I could have my new equation. And then I'm going to take this and divide everything by 2. So 3 plus 6x equals y. Guess what? That looks exactly like the first one. So for number 6, they're also dependent. All right, I think you're starting to get the point. So we've had an independent where they cross, a dependent where they're the same line, and an inconsistent where there's no solution because, well, they're parallel. All right. So let's try number 7. So for 752, you purchased 8 pens and highlighters. Like, doesn't it ask? It tells me I bought 8 pens, and the question again says, how many pens did you buy? I wonder if it meant highlighter. That's weird. All right, and some number of highlighters. And then it tells us each highlighter cost $109, and each pen, I probably should write it differently. Each pen costs 69 cents. H is actually representing the number of highlighters that I bought, and P is the number of pens, and then that's the cost. So like if I take 109 times, oh yeah, that's written wrong, times the 8 pens that I bought, no, pens are 69 cents, times the number of highlighters that I bought, and then I take the 69 cents times the number of pens that I bought. That would add up to 752. And then it tells me that I purchased 8 pens, so I know this number. Oops, I meant to actually put the number 8 in there. I'm not really sure what the point of this problem is because I don't really need the skills above. Oh, okay. I actually realized I read the problem wrong. It's probably because it's after midnight. Let me erase this. A lot of that was right, but I just don't have room. I purchased 8 pens and highlighters. They mean I purchased 8 altogether. I read it as I purchased 8 pens and some highlighters, but that wasn't correct. I'm still going to stick with the 752 equals, and then it was 0.69 times the number of pens plus 1.09 times the number of highlighters. Yeah, they probably should have said a total of 8 pens and highlighters, or I don't know. Maybe it's just because it's late. Okay, so now that's lined up, we can solve this by whatever method we want, actually. For this one, I don't really want to deal with elimination because I don't want to have to like make one of the p numbers. I don't want to have to multiply the top one all by -0.69 or -0.109, -1.09, so that I can like eliminate. What I'd rather do for this one, this is a good one where substitution makes more sense. I'm just going to solve for one of the variables. So I'm going to say p equals, and to get p by itself, I would need to subtract h from both sides. So p equals 8 minus h. And then I'm just going to take that and plug it in. So 0.69 This is where my P goes. Then I'm going to pull up my calculator because I don't want to do this by hand. 0.69 times 8. Alright, so this is 7.52 equals 5.52 minus 0.69h plus 1.09h. And we're going to subtract 5.52 from both sides. That'll go away there, and that is super messy. That leaves a 2 equals, and then I'm going to go ahead and combine these two. And as ridiculous as this is, I'm not even going to use my brain. I'm just going to use the calculator. I know that's easy. I don't care. 4h. Then we just divide both sides by 0.4. And that will be h. Again, this is way easier than I'm making it. Equals 5. And because we bought 8 altogether, the pens must be the other 3. Okay, so system of 2 equations, 2 unknowns. I'm not really sure if they meant to put that in the next section because we kind of did substitution elimination in the next section, or if they were expecting us to graph that and then find where it was in the graph. We could have done that with Desmos, but alright, so the next section is all about substitution and elimination. We did a little bit of this already, so I'm just going to do one of each. So if you want to pause and try number 10, you can, and then same thing for number 12, and we can work it together. Alright, so this is number 10. So I'm going to do this one by substitution. So I'm going to go ahead and just rewrite this with the 2y on the other side, because that's what I'm going to substitute in. And I could have picked any of the variables. I like to pick one that doesn't have a coefficient, so that when I solve it, all I have to do is rearrange. I don't have to divide or multiply. So this is called substitution because I solved for one of the variables and then I substituted it in where it needs to go. Let's go ahead and subtract 9 from both sides. Oh, mercy. My eyes are getting tired. Okay, so y equals -2. And we could plug that into either equation and figure out what x is. So x equals 2, y plus 3 equals -4 plus 3, which equals -1. So the solution of this would be -1, -2. There's my -1, there's my -2. Alright, so substitution. Solve for something, plug it into the other one. Here's number 12. Pause it if you haven't worked number 12 yet and you want to first. Alright, so for this one, we start with 2 things that are not lined up for us, and we need to fix that. I mean, in theory, we could leave that like it is, but that's just not going to work out nicely. I guess what I'm trying to say is you don't actually have to have the x's and the y's on the same side. We've been doing that, but it's actually okay. I'm going to just swap these 2 things so that I have 3 plus 5y. Notice my x's are on one side and my y's are on the other. That's actually totally okay, as long as something eliminates. And for this one, just like with the other one, once we have one variable, we can take it and plug it in wherever it is we want. And then we have our solution. And we can write that -2, 3, or we can circle the 2 pieces. Alright, let's see. Do I want to do this roast beef problem? No, I don't really want to. We have a lot going on. All right, so the solving the system of inequalities by graphing means we need to remember how to do this. I'm going to do number 16 and number 17 because I feel like those are the messiest ones. So this is kind of, oh, this is going to be lovely. Drawing's not my forte. Okay, so I'm going to sketch these but not like draw them perfectly to kind of get a feel for it. So this will be number 16. So pause now if you want to sketch or if you're good. All right, so this one is just a form of y. It's sort of like this, which we know looks like this, but we've changed, and instead of having an equals here, we have this. We'll have to analyze it, and then instead of having it be just x, it's 2x minus 4. So this gets a little bit messy because the inside part, usually what we have is we have something kind of like number 17 where it says x plus 2. We don't have a variable on the x. And so if you have one like this, instead of trying to interpret it the way we sometimes do, I recommend just making a little chart. So 2x minus 4. If I put in stuff for x, stuff for y, you can kind of figure out what it's going to be. So like, let's see, if we put in a 0 for x, we get negative 4. So 1, 2, 3, 4. If we put in a 1 for x, that would be 2 minus 4, which is negative 2. So 1 for x, we're here. How about a negative 1? Oh, what am I doing? My brain is like fried. I don't even know why I'm doing math this time. It's positive 4 because we have to take the absolute value. And then 1 is the same way. 2 minus 4 is negative 2, but we take the absolute value and it becomes positive 2. How about if we put in a negative 1? That would be negative 2 minus 4, which is negative 6, and when we take the absolute value, it becomes positive. So negative 1 is here. How about if we put in 2? So 2 times 2 is 4, 4 minus 4 is 0, and that is where we hit here. We put in 3, we have 6 minus 4, which is 2. You can see this is the point where that is like the worst dashy line ever. I'm so sorry. Okay. So there's our dashy line. To figure out what, because it's y is less than that, to figure this out, probably it's going to be down here, but let's just plug in 0, 0. So 0 for y and 0 for x. 0 is less than, this would go away, leaving me just negative 4, which becomes positive 4 once I take the absolute value. Is that true? It is true. Therefore, everything down here where 0, 0 is would be included. All right, so now let's do the other one. So we're still at number 16. The other one I can just rearrange and I can change it to be, I'm going to erase this down here. I can change that to say 5y is greater than or equal to negative x minus 1. And then I can divide negative 1 over 5x minus 1 over 5. Well, yuck. Okay, so for this one, I'm going to find negative 1 over 5. We're just going to assume it's like right there. And then the slope is negative 1 over 5. So down 1 over 5. So like right here. And this is just a line, and it has a, so up 1 over, that's really far. My graph's not super consistent with scale. Alright, so that's the second one, sort of. Y is greater than that. It hits really, really close to 0, so even though I know 0, 0 is on this upper side, I'm probably not going to use 0 for it. In fact, what I'm going to do is I'm going to take my original, just in case I made a mistake, and I'm going to plug something like 1, 1 into it. Is that true? Yes, it is. So everything above this, and I could go ahead and color over here, I guess, too. But the idea is that this area has been shaded with both green and red, and so has this, and it includes the line. So that would be the solution. You have to do these by graphing because that's just the way they work. All right, and if you notice, we kind of glossed over this a little bit. Let me see if I can pull it up on Desmos to make it a little bit easier to see. All right, so I need this. I'm not going to graph both parts, I just want to show something. So when we were graphing that one and we were entering in numbers to make it easier to do it, notice that it didn't go up or down. The vertex is still touching the horizontal axis, the x-axis, because there's nothing that has been added to the end here or subtracted to the end here. Only stuff inside has been affected, so that V still has its vertex in the axis. And there's nothing on the outside that's negative, and so we know that absolute value is going to give us positive, therefore the V opens up. The tricky part was that we didn't know how far to slide it. Usually we just take this number that's being subtracted, and if it were -4 and there were nothing here, we would just slide to the right 4. But because there's 2 here, we had to adjust that. So really what happened is if we divided by 2 on the inside and moved that 2 just elsewhere underneath, then that's kind of why it slid and hit this 2. That gets confusing trying to understand and visualize. So when you're doing these, if they have anything extra like a exponent in front of the x, just plug in some numbers. That would be easier. All right, let's look at number 17 real quick. Do I want to do 17? I don't really want to, but we're going to do it anyways. All right, so for number 17, our first one is y is less than or equal to x plus 2 minus 3. Now this one's easier, because first of all, that minus 3 tells us our vertex is going to fall on this line, because after you take the absolute value, then we shift it down 3. And this, we could rewrite this as x minus -2. This tells us that we're shifting -2 to the right. In other words, we're shifting left. So 1, 2. So right here, this is our vertex. Remember, we have the x minus h plus k, and our vertex is h comma k. So our vertex for this one is -2, because we have to think of this as x minus something. So it's x minus a -2, so that's our h is -2, and then our k is -3. So here's our vertex right here. And then there's nothing affecting the x, so it's just going to be like up 1 over 1, up 1 over 1, up 1. So it's just going to go like that. And then we could test something like 0, 0 to see where it fell. If we put a 0 here and a 0 here, what would we get? We'd get 0 is less than -3. Is that true? No, it is not true. So this is going to be the part of the graph that's colored in. All right, and then the other part of 17 was y is greater than or equal to 1 plus 1/4 x. We can rearrange that in our head to see that 1 is our y-intercept, and our slope is 1/4, means we rise 1 and we run 4. Rise 1, run 4, fall 1, go backwards 4. I'm not sure if this points exactly where it needs to be. Oh, wow, yeah. Okay, and I made them both solid because they have the equals here. underneath. All right, and then this one, let's just try 0, 0. If we put in a 0 here and a... Why did I write a 0 under the 1? A 0 here. We'd have 0 is greater than or equal to 1. Is that true? That is not true. So all of this would be the thing. Which means in this case, the only thing that... Let me expand this so that you can see this. The only places where we have actually in common stuff is like here and here. And there's like a hole in the middle. Okay, so do you understand how to do those? I'm assuming you just said yes. They're aggravating, but you can do them. Okay, this one was about the maximizing and minimizing thing that we were doing for a while. Sort of some real life stuff. So, for example, in number 20, we have x is greater than or equal to 2. So here's our x. So x, we would draw a line here. And then we would color in everything over here. And then y is greater than or equal to 0. Here's our y. And we color in everything over. And the last one is 3x plus 2y is greater than or equal to 12. This is where we have to have like a... I can't decide what color I want. No, we're going with this one. So this is where I would take my 3x plus 2y. You could just stick it in the graphing calculator. Or you could rearrange. So 2y greater than 3x plus 12. Y greater than or equal to 3 over 2x plus 6. So at this point we would actually have to have, you know, some marks on our graph. And, oh, I don't want to make more marks. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. Alright, so basically it's going like this. And I'm assuming the top's going to get colored in, but let's put in 0, 0 just to see. 0 is greater than or equal to 6, not true. So 0, 0 is not a point, so it's everything up here. Now because the red and the green, red overlapped anything above the x-axis. Green overlapped anything past 2. Yeah. Was it 2? I can't remember. There it is. Yeah, 2. And so the blue is going to be everything that is both past 2 and above this blue line. Because by default, it's above the x-axis over there. It would not include anything below this part, so it would end right here. Well, the green's not over there anyway, so that doesn't matter. Let me see if I can grab a purple so I can show you the area. So this area right here is basically the solution area. So when we want to maximize, that means we need to find the edge points of that area. To make this a little bit prettier, I think that I'm going to need to put this over here. Okay, yeah, that works. And you're allowed to use a graphing calculator if you have one, or you can draw this all out. Alright, so here's our... Oh, you know what? I just realized I made a mistake on my thing. I did not make my 2y negative when I moved it over. I mean, my 3x negative when I moved it over. That made my slope totally wrong. This blue line should have been sloping the other way. Okay, so now that we actually have it correct, let me expand this a little bit so you can see what's happening here. I'll put the keyboard down and push this away. Alright, so this blue line that I had drawn accidentally upside down is sloping downward. It has a negative slope, which sections off this area way more beautifully than I had done. So you can see that the green is everything that's up here, so everything positive. The blue is everything that's past 2, so everything going this way, which means the green and the blue overlap in everything that's here, like this box, and then going out this way. And then here's our purplish area. It starts here and it goes this way. So this would be one of our points right here, and this would be one of our points right here. The other points just kind of go off to infinity, but it's okay because this is asking for a, let me zoom in a little bit. This is, no, that only zooms in once. This is asking for a minimum. So if it were asking for a maximum, we'd be in trouble because we'd be like, well, it just goes on forever and ever and ever into infinity. So, you know, just there is no maximum. We do have a minimum because we have these 2 points right here that kind of section it off. This way it just keeps going, and this way it just keeps going. So let's look at these 2 points. This is 2, 3. This is 4, 0. So we're going to take this, and we're going to put in 4, 0 into where it says x plus 5y. I can do that in my head. 4 plus 0. That means c equals 4. Let me plug this one in. 2, 3. That would be 2 plus 15, because 2 for the x, 3 for the y. 2 plus 15, that's 17. So between these two numbers, 4 is definitely smaller, so this would be the winner. So 4, 0 would be the minimum. So in these problems where we have a system of constraints, we graph all the constraints, we color it in, we find the vertices, the areas where they kind of finish, and then we take each of those points and we plug them into the objective function, which is what this is called. If we have a minimum, we wanted to pick the smallest one. In this case, this is maximum. So if you want to try this one on your own, you're going to graph all of those, look for the vertices, and then plug those vertices into here. And whichever one gives you the biggest P is maximizing it. Okay? That's the linear programming section. Now the last 2 sections that we did are, let me make this big again. The last 2 sections that we did were the section that I just covered a little bit. So solving by elimination or substitution. There are a lot of, I don't know how long my video is at this point. We're going to do number 23. So if you want to pause the video and try number 23 by yourself, and then we'll try 25 after that. Ooh, what a mess. Okay, let's move that stuff out of the way. So number 23, if you paused it and wrote it on your paper, you would still have it. So we're just going to assume that you did that. So x plus y minus 2z equals 8. 5x minus 3y plus z equals negative 6. And negative 2x minus y plus 4z equals negative 13. And this is the one where they wanted us to do by elimination. So I'm going to pick 2 of them, this one and this one, because they both have a y that is opposite. So I know I can get rid of it. So negative x, that goes away, plus 2z equals negative 5. Alright, so there's one of my equations. Now I'm going to do the same thing. I'm going to pick this one with one of the others. Let's see. None of them really line up, but this one has just a solo z going on right here. So I can multiply that up or down to whatever. So I'll just pick this one since it's negative and therefore opposite. So x plus y minus 2z equals 8, which means I want this to be 2z. So I'm multiplying everything by 2. Go away. So negative 6 doubled, z doubled, negative 3 doubled, 5 doubled. Alright, I'm getting rid of this, which is what I wanted to get rid of. That's great. Oh, dang it. No, it's not. I wanted to get rid of the y. I'm not even paying attention. Can't get rid of a different variable. That won't help me at all. I'll still use this one, but I've got to get rid of the y. So I'm going to change the top one to 3x plus 3y minus 6z. I'm writing my 6 backwards. 6z equals 24. So I just took this top one and I did times 3 to get down here. And now I'm going to take the middle one. So 5x minus 3y plus z equals negative 6. I have 8x. The 3's cancel. I mean, not the 3's cancel. The y's cancel, which is what I wanted. And now I have two equations. And they have an x and a z only. So to solve this, I'm going to make this one be negative 8x. So everything times 8. And then I'm going to take this one and use it just as is. 8x minus 5z equals 18. The 8's go away. That leaves me with 11z equals, that looks like 112, equals negative, and then 40 minus 18, that would be 22. So z equals negative 2. And then I can take that and I can go plug it into other stuff. So like over here, I had 8x minus 5, put in negative 2 for z equals 18. Probably should have, actually, you know what? I can do that one, but I'm going to do this easier one. Negative x plus 2, negative 2 equals negative 5. Negative x minus 4 equals negative 5. Negative x, add 4 to both sides, and then flip the signs. And then you can plug that back into something. I'm going to pick this easiest one up here. So 1 plus y minus 2 equals 8. Y, this is minus 4 plus 1 is minus 3. And then y equals 11. That's my answer. And I can take my answer, I can write it in the form that looks like this. Okay, so that was the last one from the solving systems of equations using elimination and substitution. Oh, I didn't do a substitution yet. I'm tired and I think you're good at substitution. And on the test, I actually don't require you to do a specific type. You can choose substitution or elimination every time. The very last section was solving systems using matrices, but I've already recorded a video on that tonight, so if you need a review on that, just rewatch the first video. And then if you have questions, we'll talk about them Monday so that you're ready for the test Tuesday.